Chapter 6 is about continuous distributions, and a lot of that is going to be about the normal. There is some stuff in this particular section about the uniform distribution as well, and we're actually going to lead off with that because it's a less complicated shape and it's easier to get the probabilities. But in general, with continuous distributions, there are some things that are going to be kind of different, and that has to do with how many possible values there are. With a discrete distribution, most of the ones that we had, like in chapter 5, they were ones where we had a finite number of possible values. And that's one scenario that can happen, but the other would be if you had a countably infinite number, where you could still enumerate everything, like you could enumerate the possible values and there's just no upper bound. However, with a continuous distribution, you can have an uncountable number of possible values, and that is why you get this, which is kind of a weird thing if you're not used to it. That the probability of any individual number is 0. Basically, the reason for that, without getting too deep into set theory, which is really where this comes from, the idea of countably infinite and uncountable, basically it's like you're taking a step up in how big the infinity is, more or less. And I guess you could even think about it with a concrete example, like if you were looking at a distance from one city to another, and let's say it worked out to be 250 miles, then it's not going to be 250.0000000, just all repeating zeros, right? It's going to be, close to that, but it's rounded off to make it easier to understand. And once you start factoring in the idea that if with a continuous distribution, how every value in an interval is possible, then you can have like irrational distances and all these kind of crazy numbers, that the chance that you get like exactly 250, it's remote, and it actually works out to be 0. For any specific number, that's what you're going to have. So that means that instead of trying to figure out the probability of a specific value, because that's always going to be 0, and that's kind of boring, we're going to get probabilities of intervals, which in almost all cases won't be 0, at least that we're going to talk about. And then it's still the case that all probabilities have to be between 0 and 1. And then if you had an interval with all possible values in it, that probability would have to be 1, which is pretty analogous to what we have with the discrete distribution. This last part, it looks like we're going to do calculus here because of the word integral. We're not, but if you have had calculus before, there is a part of this that's kind of a natural connection, which is that, and you can see in this picture down here, the way that you figure out the probability is the area under the curve. And that's why this arrow is pointing into this region between 7 and 9 underneath the curve. And if you've had calculus before, you're thinking, okay, area under the curve, that's integration. It's not going to be that because with a uniform, you can just do it with area. And with a normal distribution, the integration is really hard, actually. You have to use an approximation. So if you've never had calculus before, don't worry about it. We're not going to do it that way. And if you want to think of it as that's what StatCrunch is for, or that's what your calculator is for, I think that's a reasonable perspective to take here. And actually, going back up here where I have this arrow for a second, there is one consequence of this that's going to feel really strange if you've never done it before, which is that since the probability of any individual value is 0, there's no difference between a less than and a less than or equal to in terms of probability. Because with the less than or equal to, the only thing is extra is that you add in the endpoint, but the probability at the endpoint is 0, so they end up being the exact same thing. Same thing with greater than and greater than or equal to. So it's not like algebra where that matters, right? Where if you're including the boundary or not, that makes a difference. Here, not with a continuous variable, and it does matter for a discrete variable, right? Like with a binomial, the probability that x is greater than 2 or x is greater than or equal to 2, those are going to be different things. But here, with a continuous variable, they're not. So, like it says here, suppose that, and I'm cutting part of this off. There we go. If X is the weekly use of gasoline by adults in North America, and this is just all made up stuff here, like these numbers. So suppose the probability that X is strictly between 7 and 9 is 0.24. Just so I have kind of a number to use as a prop right here. That's really what that's for. So that probability is saying that if you randomly selected an adult in North America, the probability that they use between 7 and 9 gallons of gas in a week is 0.24, right? And then there are some extra probabilities in here. What's the probability that a randomly chosen adult uses exactly 7 gallons of gas per week? Well, that's 0 because this is a continuous variable, right? Things that are physical measures like this, right? I mean, like this is an amount, right? It's in gallons. It's a physical measure, right? Gasoline is a liquid, so you know that's certainly going to be the case here. Then it's a continuous distribution, so the probability of any individual value is 0. So not only is this 0, so is the probability that x equals 9. And then things that are equivalent, and here's where you see the less than and less than or equal to being the exact same thing, that we could add in individual endpoints, right? We could say the probability that 7 is less than or equal to x, which is less than 9, is 0.24. Since the only thing that's different from up here is that I added in the 7, but the probability that you get 7 exactly is 0, so that doesn't change the value of that probability at all. Same thing would happen if you added a 9. So if I have the probability that 7 is less than x is less than or equal to 9, that's also going to be 0.24 since the probability that x equals 9 is 0. Same thing if you added them both in. So the probability that 7 is less than or equal to x is less than or equal to 9. That's also going to be 0.24 because with that one you're just adding in 2 zeros. Well, that does the same thing as adding in 1 0, right? Nothing. So you still get 0.24. That's a little weird, right? If you're not used to it, it's really weird that less than and less than or equal to work out to be the same thing. And that's just a quirk of continuous variables where there are so many possible values that the probability of any individual value is 0. And this is just sort of a consequence of that. Okay, next. So graphically, what you end up with is a smooth curve for a continuous distribution. I suppose you could see that in the picture, that this one over here does not look blocky and that the discrete one does. This term right here, this shows up a lot, that you have a density curve. And basically it's just that there's some function where if you graph it, that ends up being the probability distribution. And clearly this is an idealized shape because it's so perfect, and that's what the second point says. It is an idealized version of a histogram or a dot plot, and that's why I have this one over here being kind of a bell shape, right? Like from a discrete distribution, it's like, it's not perfect, but if you were going to draw like a best fit curve to it, it looks like it would be a bell shape. And then this one looks perfect, and the continuous distributions always do because they are just like these theoretical models. And let's see, so probability is the area under the curve. And with a uniform distribution, you can do it just by computing like the area of a rectangle. Because what a uniform distribution is, it's the continuous counterpart, like it says there, of having an equally likely probability model. So like for rolling a single die, all the individual probabilities are 1/6, right? That's the probability of rolling 1, rolling 2, and so forth. And this is the same thing where the probability is always going to remain consistent in the sense of like when you look at the graph, it doesn't like go up and down, right? So if you look at the uniform distribution, it's just going straight across, and that's it. And a continuous variable follows a uniform distribution if the variable takes any value in that interval and that probability density function stays constant. So graphically, staying constant is horizontal, right? So like the normal does not stay constant, which is what this is, right? I mean, even though we're not talking about it yet, this is a normal distribution, right? It's a bell curve. It goes up and then it goes down, right? That doesn't stay constant. This density function does because it's just flat. And to figure out a probability, it's just like figuring out the area of a rectangle. So this will make more sense, I think, with some numbers. So during certain time periods at JFK Airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes, like in that picture. Okay, so I guess first things first, clearly this is a uniform distribution because it's flat, right? That's, I guess, the first thing. The next thing is, why is the height 0.2? Well, because the times are distributed between 0 minutes and 5 minutes, right? So then if you're going to make the rectangle that would form this distribution, then the length of it's 5. The area of the rectangle has to be 1 because this is a probability distribution, right? And so the probability that you get one of the possible values is 1. right? You have to get one of the possible values. You can't get an impossible value. So the area of this rectangle has got to be 1. So basically, it would be like if you solved this, I guess back from like geometry or something, where area is length times width. If we know the area has to be 1, and I guess the width is going to be more like the height in this picture, but the length is 5 times W, and so then that would mean that 1/5 is W, right? So 1/5 is 0.2, right? So that's got to be the height of that rectangle to get the area to be 1, because if the area is not 1, then this isn't going to be a density function, right? This isn't going to be one that we could actually use to figure probabilities out. So that's why, right? Like that's where the 0.2 comes from. It's because we know this is going to be 5 in terms of length. Like that's right. It goes from 0 to 5 in terms of how long people have to wait. But then the area's got to be 1, and that forces the height here to be 0.2. So then we want to find the probability that a passenger at JFK waits longer than 2 minutes at the security checkpoint. Well, this is just like finding the area of a rectangle like it says. So 2 minutes is right here. So if I just I'm going to make a vertical dotted line here. And I'm going to say, all right, well, we need this then, right? Longer than 2 minutes is from 2 up to 5. So it's this part right here. And you say, well, we know how tall this is already. It's 0.2. And we can figure out the length because it's the difference between 5 and 2, right? So this length is going to be 3. So then the probability that x is greater than 2, it's going to be 3 times 0.2, which is 0.6. See? Just like figuring out the area of a rectangle. Right, and there's one dimension that you have to kind of solve for a little bit, but once you've got that one, you just multiply them together, right? Just like in geometry. All right, another example. A rescue team of a city fire department is responsible for a 7-mile stretch of river. So now it's 7 instead of 5. I guess that's the first thing that's noticeable. And the distance between the northernmost point and the location of an emergency is a uniformly distributed random variable, there we go, over the interval from 0 to 7. Okay, well then what we're going to have, if I kind of draw this picture out. So let's say if this is where 7 is, then my rectangle, which I should make this a different color, we'll go for the maroon, I guess. All right, and then this has got to go up to some number, which we're going to figure out. But we're still going to get that rectangle shape. I made this too big. I can't do it all in one stroke. Ugh, barely got there. Okay. And then I guess back here, if I switch back to blue like this, right here is 0. And then we have to figure out the height, right? But still, the area has to be 1. Right? So then you could say, well then, if area is length times width, then 1 is going to be 7 times width, right? So then the width has to be 1/7, or I guess the height in the picture, right? Just like before. So 1/7 right there. And then we want to find the probability that a given emergency arises within 1 mile. So 1 mile or closer. Okay, so I guess 1 is maybe about here. And then what we're looking for is, let me do this in a different color. Forest green, that sounds good. All right. So I'll make the dotted line there at 1 because we want 1 or less. So we're looking for this right here. And so we just have to figure out that probability. And then you say, well, we know the height is 1/7, right? And then this distance here from 0 to 1 is just 1, right? So then we could say, all right, well then, let me change the color back. The probability that, I guess it would be x is less than or equal to 1, would be 1 times 1/7, which is just 1/7. Or if you want this as a decimal, 0.143 to 3 places. Okay, one more. Same example, but the emergency arises between 2 and 4 miles from the northernmost point. Okay? I got a lot of space this time, so I'm going to make a nice big picture. So once again, we got to go out to 7. And we're going to need 2 and 4, so I think, let's see, 2 is maybe here, 4 is maybe there. I guess 7, this is not quite to scale. That 7 should be a little farther out, but that's all right. We already know what the height is, right? That's 1/7. And then, all right, so I guess I can draw in everything that we had before. All right, so then the rectangle that would be the uniform distribution, we can make that. There we go. And we need between 2 and 4. So, okay, there's 2, and there's 4, and we need this in here, right, between 2 and 4. Okay, well, the distance between 2 and 4 is 2, right? And then this right here, if I can draw this has to be kind of small. It's 1/7, right? So then the area, which would be the probability that 2 is less than x is less than 4, or if you like, the probability that 2 is less than or equal to x is less than or equal to 4, because remember, less than or equal to are the same for a continuous distribution. This will be 2 times 1/7, which would be 2/7, or I guess if you want it as a decimal, 0.286. There. Okay, so the uniform distribution is not too bad, right? It's just, if you can get the area of a rectangle, you just have to figure out from the wording how to define your rectangle that you need to get the area of, right? And you can always kind of solve for how tall it has to be, just because the area underneath the entire distribution has got to be 1. And then from there, basically you just need what your cutoffs would be. Like here, the 2 and the 4, or up here from 0 to 1. You just have to figure that part out, and then it just turns into figuring out the area of a rectangle. All right, next, the normal distribution. So this is the bell curve, right? And its properties, so it is perfectly symmetric, right? The left and right sides are mirror images of each other, bell-shaped. And as long as you know what the mean and standard deviation are, that tells you specifically what normal distribution you're talking about. Because the mean will tell you where it's centered, and then the standard deviation will tell you how spread out it is. So if your standard deviation is really small, then it's going to be like really narrow and thin and tall, right? Because the area under the curve is always 1. So if it's really narrow, it's got to be really tall. So the area still ends up being 1. And then I guess if your standard deviation is really big, if it's really spread out, and the tails are real long, then it's short. Like in the middle, it has to be short because, again, the area's got to stay 1. So if it gets stretched out this way, it's got to shrink down. But it's still going to be a bell shape. It's just sometimes you get a really narrow, thin bell shape, and sometimes you get like sort of a squat-looking bell shape, I suppose. But then the notation, a lot of times, is just written like this. So like if you were talking about the normal distribution with a mean of 5 and a standard deviation of 2, you'd see n and then in parentheses 5, 2, like that. And so that's all that that's really getting at. But then there's a special kind of normal distribution called the standard normal, which comes up a lot because you need it for confidence intervals in chapter 7, so not too far into the future. But a standard normal distribution is just a specific normal distribution. It's the one with a mean of 0 and a standard deviation of 1. So like this is the key here, where this is the thing that's easy to get confused by if you're not used to it, because it seems like a standard normal distribution, and I did an awful job circling that, that it would be something, I don't know, more exotic, I guess, but that's what it is. It's just mean of 0, standard deviation of 1. And then a standard normal random variable, a lot of times there's just a z. So instead of seeing n, 0, 1, a lot of times you just see z. And that's where the idea of a z-score comes from. So a z-score is what you get when you standardize, right? So the idea of standard normal being standardized, that's why it's a z, like z-score. So I guess that's really why that all ties together. And there is such a thing as a Z table, but I don't really think we need that. And there is one in our book, and it'll come up in the homework. Like the homework will have questions that say use the Z table. I wouldn't bother with it. I would just use StatCrunch for everything. StatCrunch is more precise, and I think it's easier. So I would just use that. So you could do it that way, but it's extra work. You also have to standardize. With StatCrunch, you don't. So we're not going to use that. We're just going to use StatCrunch. So that's how we're going to do this. We are not going to worry about the table in the back. So how do you do this in StatCrunch? You kind of go to the same place that you would go for the binomial when we had that, except that you go to normal instead of binomial. So if you go to stat and then calculators, this is where all the probability distributions are. So for binomial, we went here, but we're going to go here where it says normal. And then you get one over here with the picture, and you can toggle the probabilities and everything. And then notice that the default setting is mean of 0, standard deviation of 1. So the default is to give you a standard normal. If you want some other normal distribution, you just have to adjust these, which isn't really that big of a deal, but you would have to do it. And let's see, going back here, I did write that in that the default is a standard normal. And so for this section, that's perfect because the rest of this section is all about the standard normal. So then you just have to specify the cutoff and the direction, and then from there you click compute and you'll get it. All right, so this example, and this is sort of the classic example for something that uses a standard normal in real life, and our book uses this one too. The bone density test, that's the way that that's set up. And so this is a nice direct application where a bone mineral density test can be helpful in identifying the presence of osteoporosis. And the results are typically given as a z-score. So like from a standard normal distribution where you've got a mean of 0, standard deviation of 1. All right, so let's say a randomly selected adult undergoes a bone density test, and we want to find the probability that the result of the bone density test is, for the first one, less than negative 0.5. Okay, well, I think it helps to draw the pictures here, and that's why I have these little curves in here. And then that way, I guess you could check it against what you've got in StatCrunch. And if your StatCrunch picture looks like your hand-drawn picture, then you're probably in the right place. But I think the drawing helps. So the mean is going to be 0 if this is standard normal. So I can put that in. And then negative 0.5, you don't have to get this perfect, but it should be less than 0, right? It's a negative number. It's, I think, roughly about here. So I'm going to say that's about where negative 0.5 is. And we want a measurement less than that. So we're trying to get this over here. That's the thing we're trying to figure out. So then what we're going to do is we're going to go to StatCrunch. And the thing that we want is the probability that z is less than negative 0.5. Right? And I used z because that's a standard normal, right? So I guess I can kind of write that in here. So let's put an arrow at that z and say that's because it's standard normal. All right. And then the next step is just go to StatCrunch and adjust the cutoffs and things. So let's see, if we go to StatCrunch, it's already set up for a standard normal. We wanted less than negative 0.5. So I guess really I just have to change this. Since less than and less than or equal to are the same. Notice they don't even give you the option of a strict less than, a strict greater than here. So we'll have to use less than or equal to, which is fine, right? It's a continuous variable. Less than or equal to are the same thing. And then if you click compute, oh, I have this in the wrong spot. I need it over here, right? So this is where it would give you a probability. I was using the wrong box. I just saw the 0.5 and I was like, oh, I just have to adjust it. But it actually needs to be over here. We want the probability that x is less than or equal to negative 0.5, compute, and there is the thing that I wanted, the 0.3085. So that's about it. There are a few more in here, but that's basically the idea. So here we get 0.3085. Then the next one I think is a greater than, measurement of at least 1.35. So there's 0 again right in the middle. 1.35 is going to be pretty far out. And you don't have to get the pictures to look perfect or anything, but I mean, it should be bigger than 0, right? The 1.35. If you really want to go for precision, the values that are 1 standard deviation away, so like for a standard normal, it would be where 1 and -1 are, they're at the inflection points of the curve, if that helps. So 1.35 should be past that, and I think roughly about here should be accurate. It's about where 1.35 is, and at least would be that number or above. So we're looking for this tail now. So when I go to StatCrunch, that's the adjustment I got to make, is I got to switch the inequality around. So we're looking for the probability that z is at least 1.35. All right, and if we go to StatCrunch and do it, see, I got to flip the inequality so it's a greater than or equal to. And then I need my cutoff to be 1.35, then compute, and there we go, 0.0885. All right, and then you can look up at this picture here too and say, oh yeah, this looks like this sketch right here. So it looks like we've got it set up correctly. All right, so in a way, the picture kind of acts like a check if you draw the picture yourself when you start everything up here. So 0.885, there we go. And then in between, we have to go to a different part of StatCrunch for this, a slightly different part. You'll see what I mean in a second, but we still got 0 in the middle. 0.40 and 0.95. They're actually going to be fairly close together. I probably drew them a little too far apart, but that's all right. So there's 0.40 and I got to write those with the 0 in the front. I think that's making the picture look uglier. All right, so 0.40, 0.95. Okay, and then we're trying to get the in-between, so we're trying to get this. So, all right, go here. And for an in-between, up here where there are the options of standard in between, your default option is standard, and that's for less thans and greater thans, or less than or equal to's and greater than or equal to's. If you go to between, then you can get an in-between, and that's what we want here. So we want between 0.40 and 0.95 there, 1735. And our picture looks like the thing that we had over here, right? So we already did it this time. We went to StatCrunch and we got our probability. So the probability that 0.4 is less than z is less than 0.95 is 0.1735. Okay, I think that's everything on that page. Next page, this is interesting, like you're going the other way to get percentiles. So how do you get percentiles? Basically, this is the same type of problem, it's just you're solving for a different part. Because before, it's like you were given the cutoff or cutoffs, like in these questions, right? It's like, here's your cutoff, the 1.35, here are your two cutoffs, and you had to figure the probabilities out. These are kind of the other way around, where if you have the percentile, you know what probability you're supposed to get, and now you're trying to find the cutoff. The one thing you do have to keep straight with percentiles is that the way that they're named is by the probability that's below them. So in the picture, that would be the probability to the left. So the 25th percentile, whatever that is, it should have 0.25 below it or to the left. So I'm going to draw that, I guess, to where it's like maybe here. That seems like it's about right. Where then, if this is z, the thing that we're trying to solve for, and then back here we've got 0.25 in that part of the curve. I think, and actually I should draw this a little bit differently. I think this would look better if I shaded that in. So yeah, we got 0.25 to the left, so like over here. So like in that tail, oh, terrible arrow. We're gonna have to live with it, 0.25. And then up here, then this would have to be 0.75, right? That's above it. Since the area under the curve's gotta be 1 altogether, so 0.25 plus 0.75 will give you that 1 back. And then we're gonna use StatCrunch to do it. So we are going to use StatCrunch. So the thing that we have right now, we know the probability of, I guess, then this is supposed to be like a little z, maybe. So like big Z is less than or equal to little z is 0.25. So then like that, I guess, should be a lowercase z, right? Because that is this right here. But then we have to get little z. So how do you set this up in StatCrunch? And the reason I wrote this way is to kind of point out how you would do it and where you would put the 0.25. So if I go back to StatCrunch, we want the standard this time. This isn't an in-between. And it's a less than or equal to. And our probability, we know, is supposed to be 0.25. So this is where you enter a value in this box that's all the way on the right. Because the thing you're trying to get is here in this blank box, or at least the one that's blank now. And so then if I click compute, there it is. So that negative 0.674, that is going to be the 25th percentile, because the probability that you get something below that is 0.25. So going back here, little z ends up being negative 0.674. All right. And that is always the conventional way of writing that, like with the big Z for the variable and then the little z for the cutoff. Although it does get confusing with the two different z's in there. And I just wanted to write it out this way once so it was a little more direct as to where you would put the 0.25 in StatCrunch. I'm not going to write it that way this time because it confuses me a little bit too, even though that is the common way of doing it. So let's see, I guess we still got 0 in the middle, right? This is still standard normal. 90th percentile should have 0.9 to the left, which is quite a bit. So it should have 0.9 to the left and therefore 0.1 to the right. So maybe something like this, right? Where then there, and I guess I can change the color a little bit. We're going to have 0.1 there and then 0.9 back here, right? And then we're looking for that cutoff that'll give us the 0.9 below it and the 0.1 above it. So that's where our little z is. Then if you go to StatCrunch, then you just have to change this over here because we want the probability to the left now to be 0.9 or 0.90, and you get 1.282 to 3 places. All right, so that's about it for getting a percentile. So I guess here, probability, and I'll write it this way again, I might as well. Big Z less than or equal to little z. If that's 0.90, then little z ends up being 1.282. And then the things that are in lowercase would be that little z and that little z. All right, so in order to get the percentile, it's a similar problem, but the other way around. You specify the probability, and then StatCrunch gives you the cutoff, as opposed to before, where it was you specify the cutoff, and StatCrunch gives you the probability. All right, one last thing, and it's related to the percentiles, this idea of a critical value. This is actually a pretty big deal because a lot of what we're going to do in Chapter 7 runs on this. Because this is a big thing with confidence intervals. So for a standard normal distribution, a critical value is a z-score that functions as a threshold for being significantly low or significantly high. And usually what you're looking for then would be things that look like this. And usually what you're going to have in the subscript is a 0.025 or a 0.05 or a 0.01 or a 0.005. So I just put two of the common ones in here. The thing that's a little awkward, and this is why I was never a huge fan of this notation, because you talk about percentiles, and percentiles tell you what's toward the left, right? 30th percentile, 30% toward the left of whatever that cutoff is, right? 85th percentile, 85% to the left. But then with critical values, that alpha is what's to the right. So like z with the subscript of 0.025, that means you want 0.025 to the right. So it's not going to be a whole lot. I guess I can draw it like way out here. If that's where z sub 0.025 is, then up here, we've got a 0.025 in that tail to the right, and then it would be 0.975 back here, right? Since those two areas would have to add up to 1. So then if you use StatCrunch to get this, it is like getting a percentile. It's just that you have to remember that that alpha is what's to the right instead of to the left. But we are just going to go to StatCrunch and get it. So we need 0.975 on the left, and there's our answer. It's 1.960, or just 1.96. So z sub 0.025 is 1.96, and this actually is by far the most commonly used critical value. You'll see it when we get into chapter 7. You will definitely see it a lot. And I should point out here that you don't have to do it this way. You could specify what's in this upper right tail instead. If you switch this to be greater than or equal to, and said I want a 0.025 up there, you get the exact same number. All right, so back to the other one, 0.005. That's a really tiny little right tail. That's like this, right? Where then you got 0.005 in that tail. You got 0.995 back here. And then this is going to be z sub 0.995. And so we're going to use StatCrunch to get it. All right, so if we go back here, I guess since I have it set up for the right tail, I'll just change this and do it using the right tail. There, 2.576 is usually the way that that's written out. So it's usually given to 3 places. And when we see it in chapter 7, that's what it's going to be like. So z sub 0.9, or oops, it's 0.005, sorry. I'm actually messing it up down here as well. So yeah, so you're like reflexively, I always think to the left, not to the right. So yeah, this should be 0.005. So z sub 0.005. It ends up being 2.576. Another very common one. The other one, the third one that's really common would be z with a subscript of 0.05, which is 1.645. But I guess we'll use that one when we need it. The other thing I wanted to point out here is if you did do it the other way, so like toward the left, you had a 0.995. Same thing, right? 2.576. Okay, I think that will cover 6.1, which is kind of long. This chapter is weird. There are some sections that are really long and some that are really short. And this was one that's kind of lengthy. I think the next one actually ends up being kind of short, but we'll see.